In a world that is continually becoming more conscious of sustainable energy generation, the demand for environmentally friendly power plants is increasing. This project aims to do just that: implement a small-scale ecological microhydro plant vital to building a greener tomorrow. After a site visit to Coteel, Cornwall, as well as detailed analysis of recorded flow rates, it was determined that Coteel could produce a significant amount of green power. The following video details exactly how the system should be designed and installed should the application bid be successful. This project has been designed by Isaac Jones, Louise Kiro-Watson, Mike Jarvis, Toby and William Kemp. As a team, different aspects were divided up and given to individuals to research and then determine the most suitable design for the proposed plant. These different aspects would be marked out of 5 against the design specification. This covers all areas including cost, efficiency, aesthetics, environmental installation, impact and maintenance.
With regard to interested parties, there is the National Trust who both own the land and will require the most consultation when discussing the proposed project. Researching into the Environment Agencies revealed that there would be 4 licences that would need to be obtained to get authorisation to use the water source: fish passes, water abstraction, water impoundment and flood defence. As Coat Hill as a tourist attraction is close to a handful of local residents, it is imperative that any building works have minimal impact on the paying tourists and residents near the site, as this could hinder further proposals and cause bad publicity. Additionally, the land is regarded as an area of natural beauty, meaning the visual impact of the plants must be minimised. 4 main ideas were considered for the intake system. The most basic concept is a side intake with a lead or pipe running into the side of the river. With this being such a basic design, it makes a low impact on the surrounding environment but will only extract a low volume of water, which will be further reduced at times of low flow. The next idea is a lead or pipe running into the side of the river with an in-stream structure creating a forebay to increase water diversion into the intake. Whilst this concept will increase the potential flow of water, the in-stream structure would have a significant impact on the environment. Another idea is to use a weir with a leak running off the side of it. This would allow for an increased head, good flow of water control, and as there is already a weir in place at Coat Hill, little extra environmental impact. The final possible concept is an underwater intake, but as that would require significant groundworks to the river itself, it was ruled out. So the decision matrix and the justification of each concept has led to the use of the weir providing the best solution for the required design. After deciding upon this, a site visit to the weir at Coat Hill revealed a microhydro plant already in operation, although increasing the efficiency of the existing intake inlet would still provide the best intake for a new hydro plant and improve the existing one.
When selecting a turbine, it was decided that the multi-jet pelting wheel should be chosen because it allows a high level of control at different flow rates compared to other designs. A pelting wheel is a common turbine for low to medium heads of water and uses a series of buckets attached to a circular runner. The decision matrix that was produced shows the multi-jet pelting wheel system is superior for this project. Mechanisms such as an Archimedes screw have better efficiency than a pelting wheel, however this system needs to be compact. Other turbines such as the crossflow are not suited to low to medium heads of water, instead they require larger heads to operate their maximum efficiency. The pelting wheel crossflow are impulse turbines. The other type of turbine, the reaction type, include Francis, Kaplan and Propeller, but were ruled out for cost reasons. The decision to use a multi-jet system was taken to allow greater flexibility. When the flow rate is low, some of the jets can be shut off, therefore increasing the pressure to the others. The number of jets can vary, so a compromise of flexibility and allowing good flow rate through the individual jets must be obtained.
The sediment management is vital for ensuring the plant will continue to work over a prolonged period of time. When considering which design to choose, the most important factor was how effective it is at collecting and moving the sediment. After looking at different management systems, a settling basin was selected, as this would require little maintenance and cause little disruption to the surrounding area, as an installment is fairly easy. The principle works on disrupting river flow so that it drops sediment and then pumping the dropped sediment out of the basin at regular intervals.
Braking systems are critical to ensure that no damage is inflicted to the hydro plant during times of above average flow rates. Research was carried out to find which types of brakes are readily available on the current market. Direct braking systems that act upon the shaft of the turbine were analysed, and it was found that they would need systems or operators to control them 24 hours a day, either in the form of a human or electrical RPM sensors. This would massively increase the running costs of the plant and would make the electricity generated much more expensive. This problem has been overcome by using a centrifugal brake. This is a system that needs no external input to slow the turbine down. As the turbine shaft surpasses the normal operating speed, the brake pads are thrown out against the static drum due to the increase in centripetal force. The frictional force between the pads and the drum slow the shaft down to a normal operating speed. Other factors that showed this system would be best included simplicity of the design, as well as cost and effectiveness. It was also decided that a complete bypass system would be installed. This would be used for times when the plant needed to be put into complete shutdown for maintenance.
When deciding which type of fish pass would work best, a number of different fish pass designs were evaluated, including the pool and weir fish pass, the vertical slot fish passage, the rock ramp fishway, the fish elevator and baffle fishway. The pool and weir fish pass and the rock ramp fishway are very similar, with the only notable difference being construction materials used. From the decision matrix, a rock ramp fishway provided the best solution. This is primarily because there was an existing rock ramp fishway at Coteau Mill, which could be used requiring minimal additional construction. If a different design had been chosen, then removal of the existing fish pass and a new design would have to be implemented. In order to prevent fish entering the leat, the existing grill will remain suitable for purpose. In summary, use of the existing intake and fish pass, along with settling basin and multi-jet Pelton wheel, have been selected. This is the proposed initial design to meet the given criteria. The main focus from this point will be based on creating a complete final design, which will need to include housing, generators, and outfalls, as well as improvement to the initial designs. Based on this, the Gantt chart shows the expected timeframes for the project.